Somewhere inside a lab connected to a machine colder than deep space, a scientist just watched a computer do something no computer has ever done before. And the strangest part is that this computer does not think in ones and zeros at all. It thinks in a language so alien that even the physicists who built it are still learning how to read its answers. In the summer of 2026, a researcher at Lawrence Berkeley National Laboratory used 104 qubits on an IBM quantum processor to simulate something that has haunted particle physicists for half a century. The exact moment when the building blocks of matter itself are born out of nothing. This is not science fiction. This is a real experiment published in a real physics journal, and it may be the first real crack in a wall that classical computers have never been able to climb over. To understand why this matters, you have to go back to the smallest scale of reality that we know exists. Inside every proton and every neutron in your body, there are smaller particles called quarks, and those quarks are held together by an invisible force called the strong nuclear force. This force does not behave like gravity or electricity. It gets stronger, not weaker, as quarks move apart, almost like a rubber band being stretched. Physicists describe this using a theory called quantum chromodynamics, or QCD for short. And QCD is widely accepted as one of the most successful theories in all of physics. The problem is that nobody has ever been able to fully calculate what QCD predicts when things get complicated, especially when particles are moving and interacting in real time. That gap between knowing the theory and being able to use it is exactly where this new experiment steps in. The process the Berkeley team focused on is called hadronization, and if you have never heard that word before, do not worry, because by the end of this video, you will understand it better than most physics graduates. Hadronization is the process that happens immediately after a high-energy particle collision, like the ones that occur inside the Large Hadron Collider in Switzerland. When two protons smash into each other at nearly the speed of light, the quarks and gluons inside them fly apart for a fraction of a second, but they can never exist alone. Within an unimaginably short window of time, they recombine into new composite particles called hadrons, and this recombination is what detectors around the world actually record and measure. The specific mechanism the researchers wanted to capture is known as string breaking. Imagine a piece of elastic string, connecting a quark and an antiquark, stretching every time the two particles move apart. As you pull that string longer, the energy stored inside it keeps increasing, similar to stretching a rubber band further and further. At some critical point, the string does not just keep stretching forever. It snaps, and out of that snap, a brand new pair of quark and antiquark are created directly from the vacuum of empty space. This sounds almost impossible, matter appearing out of nothing, but it is one of the most well-established predictions in quantum field theory, related to something physicists call the Schwinger mechanism. For decades, physicists have tried to simulate this string-breaking process using ordinary supercomputers, and for decades, they have hit a wall. The reason is deeply mathematical, but the intuition behind it is not complicated at all. Classical computers store information in bits, and each bit can only be a 0 or a 1 at any given moment. To simulate a quantum system with many interacting particles, a classical computer has to track every possible combination of quantum states those particles could be in, and that number of combinations grows exponentially as you add more particles. Add just a few dozen more particles to the simulation, and the number of possible combinations can exceed the number of atoms in the observable universe. No supercomputer on Earth, no matter how powerful, can brute force its way through numbers that large. This is where quantum computers offer something genuinely different, not just faster, but structurally suited to the problem. A classical bit is either off or on, but a quantum bit, or qubit, can exist in a superposition of both states at once. When you link many qubits together, the system as a whole can represent an enormous number of possible configurations simultaneously. And crucially, quantum particles can become entangled with each other in ways that have no classical equivalent at all. The scientists working on this project have pointed out that the entanglement and quantum correlations inside subatomic systems like hadronization simply cannot be efficiently represented on a regular computer, no matter how much memory or processing power you throw at it. A quantum computer, on the other hand, is built out of the same quantum rules that govern the particles it is trying to simulate, so in a sense, it speaks the native language of the physics itself. Now let's talk about the actual hardware used in this breakthrough, because the numbers here matter. The research was led by Anthony Chiavarella, a research scientist at Lawrence Berkeley National Laboratory, and he accessed IBM's quantum computing hardware remotely through a program called the Quantum Computer User Program, run by Oak Ridge National Laboratory. This is important because it shows that cutting-edge quantum research is no longer locked away inside a handful of giant tech companies. Cloud-based. Access is opening the door for university researchers and national laboratories to run experiments on some of the most advanced quantum machines on the planet without needing to build or own the hardware themselves. The chip used in this experiment was IBM's Heron processor, a superconducting quantum chip with a total of 156 available qubits. Out of those, Ciavarella used 104 qubits, engaging the majority of the processor's total capacity for a single unified simulation. To put that in perspective, quantum computers with dozens of qubits have existed for years, but keeping over 100 qubits working together in a coherent, controlled, and useful way, long enough to extract meaningful physics, is an entirely different level of engineering challenge. Every qubit in a quantum processor is incredibly fragile. The smallest amount of heat, electrical noise, or stray vibration can cause a qubit to lose its quantum state, a problem physicists call decoherence. The more qubits you try to use together, the more chances there are for something to go wrong somewhere in the system. So how did the team manage to pull useful physics out of a machine that is still, by nature, extremely noisy and error-prone? The answer lies in a clever technique described as a scalable circuit approach. Instead of trying to directly program all 104 qubits from scratch, which would be almost impossible to optimize by brute force, the researchers first built and refined much smaller versions of the simulation, using compact grids of around 10 to 12 qubits. On these smaller systems, they were able to prepare stable, low-energy vacuum states, essentially teaching the small quantum circuit how to correctly represent empty space before any particles are introduced. Once they understood how the circuit's parameters needed to scale as the system grew larger, they extrapolated those patterns outward, expanding the same underlying structure up to the full 104 qubit system. This is a bit like perfecting a small-scale architectural model before constructing a full-sized building, using the lessons learned at small scale to guide construction at massive scale, without needing to redesign everything from zero. Even with this clever scaling strategy, quantum noise remained a serious obstacle, and this is where a technique called error mitigation became essential. Quantum computers today are often referred to as noisy intermediate scale quantum devices, meaning they are powerful enough to attempt meaningful calculations, but not yet perfect, enough to eliminate errors entirely. Rather than waiting for fully fault-tolerant quantum computers, which may still be years or even decades away, researchers have developed clever mathematical techniques to estimate and subtract out the effects of noise after the fact. One such method, called zero-noise extrapolation, was demonstrated in earlier landmark experiments involving IBM and researchers connected to Berkeley, where a 127-qubit quantum processor was pitted directly against classical supercomputers running at Berkeley Lab and Purdue University. In that earlier study, published in the journal Nature, the quantum computer actually outperformed a state-of-the-art classical supercomputer on a specific type of calculation, a result that sent ripples through the physics community and helped set the stage for exactly the kind of experiment happening now. After applying similar error correction and mitigation strategies to the hadronization simulation, the results were remarkable. The 104-qubit quantum run successfully reproduced the early stages of string-breaking dynamics, and those results lined up closely with predictions made using classical reference calculations. This agreement is critical because it acts as a validation step. Before quantum computers can be trusted to explore physics that classical computers cannot touch, they first need to prove they can reproduce physics that classical computers already understand. Think of it like calibrating a new telescope by first pointing it at a star whose position you already know. Only once you trust the instrument on familiar territory do you dare point it toward the unknown. But this experiment did not just replicate old results, it also captured something genuinely new and previously difficult to observe. The quantum simulation revealed a localized effect where part of the gluon string appeared to behave like a finite temperature gas just before the string finally broke apart. In simpler terms, right before the moment of separation, the stretched energy connecting the quark and antiquark did not behave like a perfectly ordered, cold, static object. Instead, it displayed a kind of thermal, gas-like fluctuation, a subtle and fleeting behavior that had previously only been glimpsed through restricted and simplified classical approximations. Capturing this kind of nuanced, dynamic behavior directly from a quantum processor is a meaningful step forward, because it suggests that quantum hardware may be uniquely capable of revealing physical behaviors that are extremely difficult, or perhaps even practically impossible, to extract from classical simulations alone. It is worth being honest about the limitations here as well, because good science depends on clear-eyed honesty rather than exaggerated hype. This simulation was not a full three-dimensional model of quantum chromodynamics as it exists in the real universe. Instead, the researchers simplified the problem down to one spatial dimension, and they used what is known as the heavy quark limit, a simplification where the quarks involved in string breaking are treated as much heavier and slower moving than they truly are in nature. These simplifications make the mathematics tractable on today's imperfect quantum hardware, but they also mean this experiment is a stepping stone rather than a finish line. Chiavarella himself has framed this project as part of a longer-term goal, developing the computational techniques needed to eventually simulate the full complexity of quantum chromodynamics in large subatomic systems, using quantum computers that do not yet exist but are rapidly being built toward. There is another layer to this story that rarely gets mentioned outside of specialist physics circles, and that is the sheer difficulty of even preparing the correct starting point for a simulation like this one. Before you can study how a string breaks, you first have to build an accurate representation of empty space itself inside the quantum computer, something physicists call the vacuum state. This sounds almost like a philosophical riddle, simulating nothing before you simulate something. But in quantum field theory, the vacuum is not truly empty at all. It is a seething, dynamic background full of fleeting quantum fluctuations, and getting a quantum circuit to accurately represent that background state is itself a serious computational challenge. If the vacuum preparation step is even slightly wrong, every subsequent step of the simulation, including the string breaking dynamics researchers actually care about, would be built on a flawed foundation. This is part of why the team spent so much effort perfecting their approach on smaller 10 to 12 qubit systems first, because getting the vacuum state right at small scale gave them the confidence and the mathematical blueprint needed to trust the same approach once it was scaled up to over 100 qubits. It also helps to understand just how young this entire field truly is, even by the standards of modern science. Quantum computers, capable of running any kind of meaningful physics simulation, have really only existed for a little over a decade, and useful, error-mitigated results involving more than 100 qubits have only become possible within the last few years. Compare that to a field like classical lattice QCD, which has been under continuous development by physicists using supercomputers since the 1970s, refined across 5 full decades of algorithmic improvements and hardware upgrades. Quantum simulation of particle physics is, by comparison, still in its infancy, closer to where classical computing itself stood in its earliest exploratory decades. And yet, in that short window of time, quantum hardware has already reached a point where it can reproduce established physics and begin hinting at subtle behaviors that classical methods have struggled to fully capture. That pace of progress is exactly why so many physicists are paying close attention to every new milestone in this space, because the gap between toy demonstration and genuinely useful scientific tool appears to be closing far faster than many expected even 5 years ago. It is also worth mentioning how this kind of research connects back to some of the biggest scientific facilities on the planet. The Large Hadron Collider at CERN, buried deep underground on the border of France and Switzerland, remains the most powerful particle accelerator ever built by humanity, capable of smashing protons together at energies that recreate conditions not seen since a fraction of a second after the Big Bang. Every single collision inside that 17-mile-long ring produces a spray of hadrons that must be carefully reconstructed and analyzed by teams of physicists using enormous computing clusters. If quantum computers can eventually simulate hadronization directly and accurately, that could directly improve how physicists interpret decades' worth of accumulated collider data, potentially revealing subtle discrepancies between theory and observation that current phenomenological models are simply not precise enough to catch. In a field where discovering a single new particle can take years of painstaking data analysis, even a modest improvement in simulation accuracy could meaningfully accelerate the search for new physics. There's also something worth noting about how international and collaborative this entire field has become. The Berkeley experiment relied on hardware, built by IBM, computing access facilitated through Oak Ridge National Laboratory, and theoretical foundations built up over years of contributions from research. Groups scattered across the world, from teams studying Rydberg atom simulators to groups working on lattice Schwinger models using entirely different hardware platforms. No single institution, company, or country currently holds a monopoly on this kind of research. And that broad, collaborative spread of expertise is part of why progress in quantum simulation has been accelerating from multiple directions simultaneously, rather than depending on any single breakthrough from any single lab. And if you are enjoying learning about how physics and computing are colliding together to unlock secrets of the universe, do hit that like button and subscribe to the channel, because we cover breakthroughs exactly like this one on a regular basis. To really appreciate how significant this moment is, it helps to zoom out and look at where quantum simulation of particle physics stood just a few years ago. Attempts to model string breaking using quantum hardware are not entirely new, but earlier experiments were dramatically smaller in scale. Researchers exploring similar ideas have used platforms like Rydberg atom simulators, cold atom systems, and small superconducting processors, often working with just a handful of qubits, sometimes fewer than 10. Other independent teams have explored string-breaking dynamics using different simplified models, including something called the lattice-Schwinger model, and various versions of simplified gauge, theories built on symmetry groups like SU squared or discrete Z2 lattice systems. Each of these experiments served as an important proof of concept, showing that quantum hardware could, in principle, capture aspects of string-breaking behavior. What makes the Berkeley experiment stand out is simply the scale. Jumping from small proof-of-concept systems involving a handful of qubits to a coherent functioning simulation involving 104 active qubits represents an enormous leap in engineering capability, coordination, and algorithmic design, all within a relatively short span of time. This rapid acceleration reflects a broader trend happening across the entire quantum computing industry right now. Just a few years ago, quantum processors with more than 50 stable, well-controlled qubits were considered cutting-edge marvels reserved for headline-making announcements. Now, processors like IBM's Heron chip offer well over 150 qubits, and researchers are already finding creative, scalable techniques to make practical use of a large majority of them for genuinely difficult scientific problems. This trajectory mirrors, in some ways, the earliest days of classical computing, when processing power seemed to double at a stunning pace year after year, eventually giving rise to the digital world we live in today. Nobody can say for certain whether quantum computing will follow an identical curve, but the pace of qubit count growth, combined with rapidly improving error correction techniques, suggests we may be standing at the very beginning of a similarly transformative curve. It is also worth pointing out why particle physicists in particular are so eager to get their hands on working quantum simulations. The Large Hadron Collider and other major particle accelerators around the world produce staggering amounts of experimental data from high-energy collisions, and every single one of those collisions ends with a spray of hadrons flying outward in different directions. Right now, physicists rely heavily on phenomenological models, essentially educated guesses built from decades of accumulated experimental data to predict how those sprays of particles should look. These models work reasonably well in practice, but they are not derived directly from the fundamental equations of quantum chromodynamics. Instead, they contain adjustable parameters that are tuned to match past experimental results, meaning they do not universally describe every type of experiment or every energy regime perfectly. If quantum computers can eventually simulate the full real-time dynamics of hadronization directly from first principles, physicists would gain an extraordinarily powerful new tool. They could test whether unexpected patterns showing up in collider data are simply the ordinary expected outcome of known physics, or whether those patterns might be hinting at something new, some undiscovered particle or force that current models cannot account for. This is not a small detail buried in academic literature. This touches directly on one of the biggest open questions in modern physics, the search for what many physicists call new physics, meaning particles, forces, or symmetries, beyond the well-tested standard model that has dominated particle physics for the last 50 years. There is also a fascinating, almost poetic layer to why quantum computers are particularly well suited for this kind of research. Quantum entanglement, the same strange, spooky-sounding phenomenon that once puzzled Einstein so deeply that he called it spooky action at a distance, turns out to be central to understanding how hadronization actually works at the deepest level. Some researchers studying this field have proposed that as quark-antiquark pairs are pulled from the vacuum during string breaking, they inherit quantum correlations directly from that same vacuum, creating a form of spin entanglement right at the moment they are born. As the string keeps breaking apart repeatedly, additional degrees of freedom get introduced into the system, and this process can gradually cause a kind of quantum decoherence, where those delicate entangled correlations slowly fade or scramble. Remarkably, this theoretical framework has recently been used to help explain real experimental measurements of certain particle spin correlations recorded at major collider facilities, connecting deep quantum information concepts directly to observable, measurable collider data. In other words, the very same strange quantum weirdness that makes quantum computers powerful also appears to be woven directly into the fabric of how matter itself comes into existence during high-energy collisions. Stepping back even further, this entire story fits into a much larger and more exciting narrative about the future relationship between quantum computing and fundamental science. For years, public conversations about quantum computers have often focused heavily on their potential to break modern encryption systems, or their promise for optimizing financial portfolios and logistics networks. Those applications are real and important, but this Berkeley experiment highlights a quieter, deeper, and arguably more profound use case, using quantum. machines to directly explore questions about the fundamental nature of reality itself. Instead of just processing information faster, quantum computers built on the same physical principles as subatomic particles may eventually allow us to directly observe and interact with physics that has never been directly observable before, physics that exists only in the realm of theoretical equations, because no classical machine could ever calculate it. Of course, skepticism remains healthy and necessary here, and serious researchers working in this space are the first to admit that today's quantum hardware still faces enormous challenges before it can be considered fully reliable for large-scale scientific discovery. Error rates remain relatively high compared to classical computing standards, and scaling up from 100 qubits to the thousands or millions of qubits that would eventually be needed for full-scale, unsimplified quantum chromodynamics simulations represents a massive engineering undertaking, one that may require entirely new breakthroughs in fault-tolerant quantum computing architecture. Researchers in this field are cautious by nature, and rightly so, careful never to overstate results or promise timelines that the technology cannot yet support. But cautious optimism is very different from empty hype. In this particular result, a working 104-qubit simulation that both reproduces known physics and reveals a subtle, previously elusive gas-like behavior in gluon strings, represents genuine, measurable, peer-reviewed scientific progress. If you zoom out to the widest possible view, what this experiment ultimately represents is a new kind of scientific instrument being born in real time, right in front of us. For centuries, humanity's understanding of the universe has been shaped by whatever instruments we could build to observe it, from Galileo's simple telescope revealing the moons of Jupiter, to modern particle accelerators smashing protons together at nearly the speed of light. Quantum computers may represent the next major instrument in that long lineage. Not a telescope pointed outward toward distant galaxies, nor an accelerator smashing particles together violently, but a carefully engineered machine that mimics the deepest quantum behavior of nature itself, allowing physicists to essentially run a miniature, controllable version of subatomic reality inside a chip cooled to temperatures colder than outer space. It is genuinely remarkable to consider that the same strange quantum rules responsible for phenomena like superposition and entanglement, concepts that once seemed confined entirely to abstract theoretical. Physics classrooms are now being harnessed as practical engineering tools to answer real, unresolved questions about how matter itself comes into being. The 104 qubits used in this Berkeley-led experiment did not just crunch numbers faster than a classical machine could, they behaved in a very real physical sense, like the very particles and forces they were simulating, entangling, fluctuating, and settling into new configurations in ways that mirror the strange quantum nature of the universe at its smallest scales. As quantum hardware continues its rapid climb, adding more stable qubits, refining error mitigation techniques further, and developing smarter, scalable circuit design strategies like the one used in this very experiment, it seems increasingly likely that today's simplified, one-dimensional heavy quark approximations will eventually give way to fuller, more complete simulations of quantum chromodynamics in 3 dimensions, capturing dynamics that no supercomputer built out of classical silicon transistors could ever hope to replicate, no matter how large or how fast that supercomputer might become. It is easy to forget, amid all the technical detail, that every single one of these advances traces back to a very human curiosity, the simple desire to know what matter actually is and how it comes to exist in the first place. Long before quantum computers or particle colliders existed, philosophers and early scientists asked the same basic question, wondering what the universe is truly made of at its deepest level. Today, that ancient question is being answered not with pure philosophy, but with superconducting circuits cooled near absolute zero, careful mathematics, and 104 qubits working together to recreate, in miniature, the exact instant when matter is born. For now, this experiment stands as a genuinely important milestone, a carefully validated demonstration that a quantum computer, still admittedly imperfect and still very much in its early stages of maturity, can already begin to touch a corner of physics that has stubbornly resisted classical computation for decades, somewhere between a superconducting chip cooled near absolute zero and the ancient, elegant equations of quantum chromodynamics first written down more than 50 years ago. A bridge is quietly being built, 104 qubits at a time, connecting the strange mathematics of the quantum world to the deepest mysteries of how matter itself is born. And that bridge is only going to get stronger from here, as more national laboratories, universities, and research institutions gain cloud-based access to increasingly powerful quantum processors. Expect to see more. Experiments like this one emerging at a faster pace, each one chipping away a little further at problems that classical computers simply were never built to solve. The story of quantum computing and fundamental physics converging is still in its opening chapters, but if this Berkeley-led breakthrough is any indication, those opening chapters are already proving to be extraordinarily exciting, and the chapters still to come may end up rewriting our understanding of how the universe assembles itself, one quark, one gluon string, and one qubit at a time. It is also worth taking a moment to appreciate just how strange it is that a machine built to simulate abstract subatomic physics still needs to be treated almost like a living, breathing organism in the lab. Superconducting qubits, like the ones on IBM's Heron processor, only function correctly when cooled down to temperatures just a fraction of a degree above absolute zero, colder than the depths of interstellar space itself. Entire dilution refrigerators, towering pieces of engineering filled with layers of shielding and cooling stages, exist purely to keep these chips isolated from the smallest traces of heat or electromagnetic interference. A single stray vibration, a nearby electrical signal, or even cosmic ray interference from outer space can be enough to disturb the fragile quantum states stored inside the processor. Running a stable 104-qubit simulation inside an environment this delicate is not just a triumph of theoretical physics, it is also a remarkable feat of applied engineering, materials science, and precision manufacturing working together in perfect coordination. This also helps explain why progress in quantum computing tends to arrive in careful, incremental steps rather than sudden, dramatic leaps. Every added qubit increases the complexity of keeping the entire system stable, and every new algorithm has to be tested extensively at smaller scales before researchers dare to trust it at larger scales. The scalable circuit approach used in this Berkeley experiment is a perfect example of that philosophy in action, building confidence gradually, layer by layer, rather than gambling everything on an untested leap straight to 100 qubits. This same philosophy echoes throughout the broader history of scientific instrumentation, where each new generation of telescopes, particle detectors, or supercomputers has typically been built by carefully validating smaller prototypes first, refining techniques, and only then scaling upward toward increasingly ambitious goals. Looking ahead, researchers in this field are already discussing what the next milestones might look like. Some hope to extend these kinds of simulations beyond one spatial dimension, moving toward 2 or even 3-dimensional models that would far more closely resemble the real, messy complexity of quantum chromodynamics as it actually exists inside protons and neutrons. Others are focused on relaxing the heavy quark approximation used in this experiment, working instead with lighter, faster-moving quarks that behave more realistically, though this introduces even greater computational demands. Meanwhile, hardware engineers across the industry continue racing to increase qubit counts, improve coherence times, and refine error correction schemes, all of which will be necessary before truly large-scale, fully realistic QCD simulations become possible on quantum machines. None of this progress happens in a vacuum, so to speak, and it is worth remembering that experiments like this one build directly on top of years of earlier groundwork laid by many different research groups working on many different platforms. Earlier studies exploring string-breaking dynamics using Rydberg atom simulators, superconducting qubit arrays, and even ultra-cold atom-based quantum simulators each contributed important pieces of the puzzle, testing different approaches to representing gauge theories, different error correction strategies, and different ways of preparing complex quantum states. The Berkeley experiment stands on the shoulders of that broader, ongoing global effort, representing not an isolated breakthrough, but rather the latest and largest step forward in a steadily advancing scientific frontier that has been building momentum for the better part of a decade. If this kind of deep dive into the frontier of quantum computing and particle physics fascinates you, make sure you are subscribed to the channel, because there is a lot more where this came from, and the pace of discovery in this field is only accelerating from here.